much. So without further ado, I'd like to introduce Maruf Adewale. He's a medical physicist and postdoctoral research fellow at the University of Pennsylvania. And he's also doubling as an executive director of the medical artificial intelligence, today he's connecting from Lagos, Nigeria. And through initiatives like BraTS Africa, he is advancing global health by promoting dataset collection and development of AI driven medical solutions in resource limited settings. And maybe after the session, I'll send a link to a podcast where he shared more about his background and what he has achieved together with Dr. Nzoro. So yeah, it's a pleasure to have you here, Maruf.
Thank you so much, Nicola, and thank you so much for inviting me. It is an honor to be able to talk about my experiences, and hopefully it interests someone and ginger them to be better at what they're currently doing. I would like to share my screen now. I don't know if I have sharing right yet.
Yeah, you should be able to share your screen. You have sharing rights.
Okay, so today I'll be talking about the W5 of BraTS, as we all know. The main essence of the Fast-track-to-MICCAI program is for BraTS. But before I do that, I also want to quickly paint a background around exactly what is BraTS. BraTS means Brain Tumor Segmentation, and it has been running in MICCAI since 2012. And in 2023, the challenge expanded beyond the conventional glioma segmentation to involve other kind of neurological diseases too, including metastasis, including breast cancer, including pediatrics. And it also expanded to synthesis as well, where we are able to synthesize other imaging mode, other sequences from just the conventional T1, T2 to get other sequences as well. And one notable challenge that was included in 2023 was also BraTS, which is being run for the fourth time this edition. And to make sure that people get to participate very well in these challenges. The main reason why we're having the this Fast-track-to-MICCAI challenge. And as far back as 2023, when the challenge sprung from the conventional glioma segmentation, we had 991 registered participants from 97 teams who submitted 1,300 submissions during the validation phase. And this is the spread of where those submissions are coming from. And this is as far back as 2023. Now imagine what will have happened in 2024, 2025, and currently in 2026. So what I'm saying in essence is that this is a global challenge, and with a lot of interest from across the board, from resource constraints settings, from resource sufficient settings. People are participating in this challenge, and it is really important that one have a really robust solution to be able to participate in this challenge effectively. The subject of the matter itself, which is the METS challenge, the whole idea is that when patients have brain tumor, it comes in grades, grade 1, grade 2, grade 3. Even if they do not have primarily brain tumor, assuming they have prostate or they have breast, one of the de facto primary sites of metastasis, there are three. We have the brain, we have the lungs, and we also have the spine. And by default, it is always very difficult to assess the spread of these metastases in the brain. Oftentimes, radiation oncologists who might want to perform either stereotactic radiosurgery or whole brain irradiation need to know the specific sites of where these mets are before they could be able to decide what plan of treatment to administer. And it is always difficult to do this because oftentimes most of all the metastases as microclinical or subclinical, they are yet to have so much prominence for them to be identified, and or they are too tiny for either the neurologist or the radiologist to identify them. So they get easily missed. And this kind of easily missed meds, they are very difficult. It influences the kind of treatment the radiation oncologist or the general oncologist can prescribe in that case. So it is really important to find an effective way to determine if there is presence of metastases in the brain and to what extent are these metastases. And that's one of the features or one of the reasons why the METS challenge was established, to enable us to not only identify but to also monitor metastatic brain diseases and also identify how best to treat them. So the goal is to use machine learning approach to automatically detect and segment where those metastases are, and also to enhance time efficiency, to make sure it is very effective to do so. So I participating in the challenge. We're expecting you to develop an auto segmentation algorithm that reliably detects and precisely delineates brain metastases or failing sizes in pre and post treatment cases. And this is the typical example of the cases you'll be familiar with. Majority of them would be probably broadly defined, where you have your tumor broadly defined, you have the tumor core, as in the case of sample 1, size 1. And for each tumor, it is really expected to have the tumor core, then to have the surrounding hyperfly intensity, and also the surrounding no, the tumor core, the enhancing tumor, and then the surrounding hyperfly intensity. And then in cases whereby there has been some craniotomy, you also have the resection cavity being defined. But in the case of a typical tumor, a typical MET, it might not really follow this idea, but you'll be able to still see the hyperfly intensity in the presentation of the MET in the brain. So the whole idea is still to get your brain segmentation algorithm to be able to identify wherever the MET might be in the brain, even up to the microscopic or submicroscopic level. And you will be presented with almost 2,000 data sets, 1,496 of them for your training, 179 for your validation, and 303 for your testing. And for the testing, it wouldn't be revealed to you. You only know, we only use this testing to assess all the results that have been submitted by various participants of the challenge. And please understand that while you are a participant of the Fast-track-to-MICCAI program, there are still going to be other participants who are not part of this program, but who also be submitting their solutions to make it to this challenge as well. So we still have to maintain fairness in evaluating each and every one of them to ensure that everybody is treated fairly. So the testing data sets will not be revealed to anyone. The validation data sets will be released to you, but without the ground truth. The ground truth will have been loaded on the Synapse platform, whereby immediately you upload your validation submission segmentation. It compares it to the ground truth that already exists on the platform, and it is able to provide a quick assessment for you. The validation phase is what will lead you to the testing phase. And before then, you also the training set is already on the Synapse platform for you to download, including both the imaging and also the segmentation, 1,496 of them for you to be able to run your training. So now we go into the subject of discussion for today, which is what exactly can you do that can lead to a winning algorithm for you to be able to win this challenge. Now, I categorize them into four basic categories. And while you can work on a specific category, you can also combine these two categories together. The first one is input processing. Then we also have parameter optimization, then post-processing, and also network architectures. While I put various examples under each one of these categories, they are not limited to the examples I put here. For instance, under network architecture, we still have NN units now, which is a uh, sub subset of unit itself. We still also have, transformer base is also here as well. But to start with, input processing typically means you look at your data sets before it is being fed into the deep learning network. Okay, but before I do that, I would like to explain this unit that I have here. It typically starts with your imaging being fed into a unit architecture. A unit architecture typically have three sections, which is the contracting part, the bottleneck, and also the expanding part before you finally have your concatenation, then you finally have your output, typically through a softmax, and then your segmentation. Now, from your inputs, which will be released for all the challenge participants by the challenge organizers, it typically is accompanied by a ground truth segmentation. Oftentimes, some of them might be so detailed that the U network you are feeding it into might be unable to understand it properly. So it is required in such instances that you find a way to establish a direct level of understanding between the imaging data set and the input section of your method. And that is what exactly we do by input processing. In some other cases, we've had to do augmentation. And what augmentation typically do is when you have low sample sizes and your deep learning method or your input section expects a high volume of data sets, you can use augmentation to increase the number, like do some synthesis to increase the number of images you have before feeding it into the model. And when you do that, it increases the accuracy of the system. Another thing is cropping whereby you crop out some unnecessary parts, or all those black spaces that typically accompany your image. They can be cropped out. By default, all images in BraTS challenge are skull stripped, but when you are faced with data sets that are not skull stripped, you will be expected to perform this skull stripping, and in doing so, you would have been able to remove things that could confuse the method. Scaling is also used, and by scaling and also sharing, we kind of just manipulate the existing images for the model to be more accurate whenever you expose it to new testing data, for it to be able to look beyond the physical presentation, and it gives the model the ability to still detect findings based on irrespective of the presentation that you are putting into it. So the typical examples for input processing, they are not limited to this. As I mentioned earlier, you could make further findings to look at what innovative approach you can use for your input processing before it is being fed into your deep learning method. In the same space, you'll be presented with T1, T2, flare, and contrast enhanced. In some deep learning method, I've seen them only working with T1 and T2 to perform their segmentation as well, and it is quite accurate too. So you might really want to consider what kind of deep learning method you are using, what architecture you are using, and what are the limitations and what are the kind of inputs it requires. So I'll still be talking more about architecture. The next thing I would like to talk about is on your parameter optimization. So for a deep learning model to train effectively, it needs to have a an optimizer and also a loss function and also a learning rate. These are parameters that have to be preset for the method, for the deep learning method that you are currently training to work effectively. For instance, learning has to be done at a pace, and that's why we do learning rates. If it is too high, it doesn't really take a feature. If it is too little, if it is too slow, it does it at a very slow speed that you might end up spending weeks or even months in training a model. And at the end of the day, it doesn't necessarily increase its accuracy. So you might want to iterate through the different options that exist for your learning rates and the learning schedule to define which one of them is best used for the kind of training you're currently doing. The next thing I also like to talk about is on your loss function. So the essence of loss function is that when you are doing back projection and you are trying, while training in this context, and you are trying to identify the difference between your prediction and your ground truth, loss function helps you to compute those differences and feed it back into the training method for it to account for that difference that was earlier defined. So, and by implementing this loss function, you are able to go through to train it effectively. And various loss functions exist. We have the FASTkey, we have dice loss, we have lossless, and all these loss functions are already preset in your either PyTorch or your TensorFlow Keras. So you could just go to the loss function category of this particular whatever library you are using to do your deep learning training and iterate through the various loss functions that you have. When you do that, you identify the one that is most peculiar or most useful for the job that you have at hand. In the same space, we also have optimizer. Optimizer is more or less like a learning scheduler that helps you to um, properly train your model. And even though the most common one is Adam, and there's also Nadam, there's also Nestrov. Okay, that's Nestrov Adam. There are about 10 or different examples of optimizer. It also exists as part of the libraries for deep learning methods as well, Keras, PyTorch. So you can just go through the library module on their documentation and define which one of them you would like to use and proceed with that moving forward. In the same vein, I would also like to quickly talk about post-processing. Specifically, the most common one of them is edge refinement. So what happens in post-processing is that after you've got to obtained your segmentation output, when it has come out of your deep learning method, it typically have jagged edges, and those jagged edges are not consistent with the presentation of the tumor. So post-processing helps us to refine those edges in a way that it closely mimic the typical presentation of edges on a typical tumor. So there are different methods to also do this. I implore you to also conduct further findings on them, on seeing what kind of post-processing can help you to identify the best kind of edge refinement you can use that could help you to fine-tune, more like a refined edge task for you to be able to have a very accurate segmentation. And last before the least, network architecture. So UNet has really gained the ground in the areas of network architecture, but there are still a whole lot of network architectures that are gaining prominence too. Transformers have really been very prominent in doing this task. And one thing I would advise is that it is really important to define what network architecture you are going to be using. And what helps you to do that is, number one, the kind of compute you have access to. For instance, we've had to work with lightweight 3D units, even though it is not accurate, but for the task we use it for, then the compute resources we had was extremely limited, and that was what that computing space can acquire, can accommodate. So we had to use lightweight. So in this space, I am aware that you'll be provided with compute resources. So that shouldn't be a challenge. Another way to look at what kind of compute network to use is that if you look at neural IPS abstract or ICLR or ICML, all those deep learning conferences, you could easily stumble on a state-of-the-art architecture that's recently been developed in a lab, and you can bring it into medical imaging space. So that is also welcome. For instance, UNet and VNet were not originally something that was developed to only work for medical imaging. They were just meant for traditional deep learning work, and in the process, people felt that this could work for medical imaging, and it worked. So if you are looking for innovative deep learning architecture as well, you could consult those traditional deep learning conferences, and you could have an idea of what to do moving forward in that space as well. So once you have your deep learning network that you want to use, I would recommend you train a baseline model with it first. I'll still be talking about the importance of the baseline method first. What baseline training typically does is that it helps you to walk through the code line by line from end to end. It means you are able to input your image into the network and also get an output. And you are also able to compare your output with the ground truth you have and also get your metrics. What that does is that any other innovation you've done or any other tweaks or any other ideas you've implemented, you have a baseline to compare your methods with. For instance, if you implemented your baseline and it was 0.8 die score, and you implemented some post-processing method, and you run your evaluation as well, and you got it 0.85. That way you could be able to say your post-processing has worked because there is an increase in the die score coefficient. And in the same vein, if it is less than that baseline, it means that the method you implemented did more harm than good. So that way you wouldn't recommend implementing that method moving forward. So the whole idea is that while doing all this work, it is essential to have a baseline method and a baseline metric that will serve as your threshold. And that threshold is what you are going to be using in comparing whatever new methods you have with what you initially have. And that way you could be able to determine what innovation you made or not, what innovation you made or implemented, whether it works or didn't work. So I also want to talk to you briefly about the benefits of participating in the BraTS challenge. It is not sufficient only that you participate in the Fast-track-to-MICCAI program and finish it at that. It is really important that you work assiduously and get your submissions across to the MET challenge. Now, when you do that, you'll be throwing your heart into the ring in the midst of researchers globally. And by doing that, you'll be also be increasing your ranking among these professional colleagues. It's also an avenue to find new collaborators, and in the same vein, you'll be recognized for all the work that you do. There's also monetary gifts for each of the challenge, and I'm aware that MET also have its own monetary gift. So if you are passionate about what you are doing, all these benefits are things that they are like low-hanging fruit that could easily come your way. And what I've seen in years of doing BRAT is that it's always no matter how hard the challenges can be right now, it is always like a stepping stone because there are bigger things to be done. I've seen people who started with participating in program like this, who went on to submit their solution into a particular challenge, going on later on to submit to built solutions that was accepted in the larger MICCAI conference, and also participating in various challenges, even though they started with one. They've grown in their competencies, they've grown in their own dexterity, and they've also been able to attract bigger and better opportunities to themselves as well. So I just want to briefly mention about what are the things you can do that could help you ensure victory in this particular project. And the first one has been done for you already through the Fast-track-to-MICCAI project, and that is forming or joining a strong team. In addition, you've also been provided mentorship to be able to navigate through this course of participating in the challenge. Having a strong team really helps you to navigate this. In the same space, it is always nice to have both technical expertise and also clinical expertise on your team to be able to do this. Technical guys would be involved with writing the code, and the clinical guys would help to assess the feasibility of whatever method or the practicality of whatever approach you are implementing in the clinics. The next thing, which I also like to talk about, is getting access to computing resources, which has also been done for you through this program. So I don't expect you should have any challenge in that regard. One very important thing is looking at the latest advancements in this field. I've mentioned it earlier that if you are really looking for a state-of-the-art network to use, because it keeps evolving, it is an ever-evolving field. Currently, we have NNUnet, but I'm aware, I think about 2 years ago, NNUnet became prominent. But I'm made aware that there are new models that are actually rivaling NNUnet at the moment. So you really want to research those state-of-the-art method and make it your own baseline. The secret about that is that when you implement an already popular method, you are sure to have a baseline that is extremely accurate. Even if you implement an innovation that doesn't really do much, the baseline that you implemented and implementing it on this new set of data sets presents a novelty in its own. So, for instance, when the first time we did BRAT Africa and somebody implemented an engineering on BRAT Africa, even though there was really nothing novel or that they had to do on their own part, but no one has ever implemented an engineering on BRAT Africa before. So that's in its own stands as an innovation. And for the fact that NNUnet is already a very strong network on its own, they have some pretty high dice score, and they were considered as part of the winning team for the challenges we've had in the past. So I would really recommend that you look at the existing state-of-the-art method that is highly accurate and robust, and use it for your baseline. And from that baseline, you can now start thinking about what are the tweaks that you can implement that would help you to have that could make the model perform better or more accurate than it currently is. Experimenting with different techniques also work. I've learned to always iterate through different ideas and see which one of them work best. The truth is that it is only the ones that work that get published. No one really talked about the ones that didn't work. And in most cases, you have to experiment with 10 ideas before one will work. So I will recommend that you try as much as possible to have a database of different techniques and start iterating with each one of them before you finally get the ones that work, that are worthy of presenting to the larger audience. I've talked about this earlier on, versatile baseline configuration. That is extremely important, and that is the secret of success. And last but not the least, enjoy the process. To me, coding and fine-tuning and experimentation is fun. If it works, fine. If it doesn't work, it presents a unique challenge. And luckily, we have GPT nowadays that you can easily copy and paste whatever your error code is, if you're unable to troubleshoot it yourself, and put it on GPT, and it introduces, it gives you different suggestions about what the kind of intervention you can do for you. In the early days of programming, we never had this kind of flex, but it is a thing right now, and I think this is one of the um, good ways with which we can use LLM methods. So that is all today for me. Thank you so much for listening. I would like to take questions at this point. Thank you.
Thank you very much for Maruf for this gentle introduction on um, how the participants can use baseline models and what can they modify in order to squeeze out some additional performance, and how to make something different in order to compete with other participants. I think it was comprehensive, but at the same time not overwhelming. So it was great. We have a question from Amir.
Yes, Doctor. So first of all, I want to thank you for the wonderful presentation. It was very useful and gave a very great insights. So about the wonderful demonstration that you have shown in regard of the entire process of the thinking and like the training parameters and the network architecture which you have gone through. So for the training parameter part, so I was wondering how we should think when we want to select like the most appropriate loss function for like the training we want to do in order to differentiate between, for example, the non-enhancing or small enhancing tumor regions for the competition, or like, for example, is there necessarily a big difference when we are using models like ADAM, which you mentioned, or SGD or ADAM-W when it comes to like choosing training parameter for our datas, and also for the network architecture. So can we call it basically it really comes down to the term of how sophisticated of a computer we will have when we want to, for example, imply UNet or VNet, or you mentioned the transformer-based architectures as well, or we can just play with what our current computer can have and still get the same performance and result with what is in our capacity, or there is a specific requirement if we have a very highly computing device that necessarily means we will get pretty much similar result as well. And yeah, then there was like one final question, like the post-processing part that you mentioned basically will affect our boundary metrics, right? If I'm correct, like the dice score and the Hausdorff distance that you mentioned, like this is in regard of the post-processing, or there is more to it? Yeah, that was all my question. Thank you.
Okay, thank you. Yeah, so the thing with refining the edges is that, let me start from the last question. Refining the edges is that they are typically jagged edges. You know, your segmentation is being done on a pixel by pixel level, right? But those pixel by pixel levels, sometimes they can be so jagged that they don't closely represent the boundary of the tumor. The boundary of the tumor is typically smooth, like those tissues are connected to each other and separated by one layer or the other, not jagged. So while post-processing is improving the die-score coefficient, it is also helping your segmentation to closely resemble the actual thing in the brain, to make it more realistic. So that's one. In the same vein, since you are working in a competition, refining your edges can help you get better metrics, but it has to be done carefully, because refining it too much too can make it go out of scope. So you really want to be careful with the extent to which you implement those edge refinement. So that's that. On the computing resources you mentioned, the testing will be done on a super high computer. So you really do not have any limitation on what kind of, I assure you that irrespective of the kind of computing your resources you have access to, you did your training on, you did your inference on, by the time you make your submissions, the challenge organizers will still be able to assess those methods as long as you submit it through the right way using the Docker container, as long as you submit it through the established protocol, it wouldn't be a challenge. But what I have learned that using high resources, high compute resources does is that it enables flexibility. For instance, when I started doing this work, I had only one Core i7 laptop, and every time I try to run my training, it always tell me out of memory error. So it's presented a limitation because I couldn't experiment with various ideas. So having access to a large computing resources is a big flex, and I would really advise you use it judiciously. So to the first question you mentioned about the optimizer. So they currently exist, and what I typically do is that I iterate through each one of them, and that's where having very huge computing resources too also comes in. So because it's able to run the training quickly and also very fast. But before doing that, I do not suggest it to the whole of the data set. I just take, like, maybe you have 1,400, you can just take like 100 images selected randomly, or the first 100, and you do the training on them, since you are still trying to identify which one of them is best. So if you select the first 100 images, you run through all the optimizers while keeping other conditions constant. The other loss function learning rates, you make them constant. You run through all the optimizers, you rank them. You can have like you have your top result. You do the same thing for loss functions too. You keep the optimizer and other parameters constant, and you do that for them. So you are able to do this quickly and identify which one of them is best. And when you do that, you now select the best optimizer with the best loss function, with the best learning schedule. You now run another method again. When you run that inference, you are bound to get a very high score that is bigger than all the other inferences that you've been running, all the other trainings that you've been running. So when you have this, you establish it as your baseline as well, then in combination with any other tweaks that you might want to use. So those are my comments.
Thank you so much. And thank you for the wonderful answers. Appreciate it.
Any question?
I had a question regarding the training part. Like, for example, uh, do you think in these kind of challenges, semi-supervised learning can be beneficial, or like is supervised learning strategies would be better in these kind of challenges, like especially for generalizability or other cases?
Okay, so my understanding is that typically whatever you do, you should be able to report it back to the challenge organizers, whatever intervention you do. If you have to use different data sets. But I do not think that doing fine-tuning on an already existing ML method, like all those med gamma, is encouraged. We are looking for ingenuity in architectural design, and that's why you are provided with the data sets. we are looking for structural innovation, not just working, even though what we recommend is still based on what others have done and building on it, but using an existing method and just training it with the data sets, it's really not a good idea. What I would recommend is we train from scratch, you work with an existing architecture, you implement that architecture, and if you have to augment those data sets, either you have to copy data sets from other challenges or from another source, they have to be explicitly declared. And I'm aware that some challenges don't even allow that at all. They don't allow mixing other data sets. So you might want to carefully review the documentation of the challenge and see if that provision is allowed. But my recommendation would be that you do everything you want to do from scratch, because you'll still be writing a manuscript. So you would have more details to write about if you do everything by yourself compared to doing semi-supervision. Does that answer your question, Madi?
Yeah. Thank you very much for that answer.
Yeah, just to add a little note, semi-supervised training could be beneficial, but it's more beneficial for, correct me if I'm wrong, for real-world applications when the data is scarce and you want to find way to just increase the amount of data on which you're training your algorithm to achieve better generalizability and applicability. So yeah, for the purposes of the challenge, the data sets that are allowed for you to use for training is actually one data set that you downloaded the last time. And yeah. I have a question, Maruf. Have you found yourself in a situation in which you do so much of fine-tuning and post-processing that actually led to you to actually led to decrease of performance compared to baseline rather than improvement?
Yeah. So I mentioned earlier that we only get to talk about the success we recorded and not the failures. So if those refinement has to be done, they should be done economically, because if you overdo it it messes up the whole thing. So you really do, it's a scale. You can actually ask it's like a filter. You can alter the rate with which you want it to implement all those refinements. So if refinement is to be done at all, it has to be done mildly, not excessively, because it could also overdo it too. I mean, it's up to the extent of start making all the tumors into perfect circles, and we know tumors are not circles, so that way you'll be going out of context. Yeah.
I understand. Yeah. Well, I hope that throughout the next 2 weeks we'll get a sense on what to modify and the level that we need to not overcross, so that we have just a basic understanding of what there is to modify.
Yeah, true. It's all about
I really hope that we get
experimenting with
this.
it. It's all about experimenting with it, see what works, see what doesn't work, and keeping a very good record of them. And in the process, you see what works, and if you identify them, you just combine them together, and you have a winning solution. It's just about experimentation and iterating and beyond. Yeah.
Yes, that sounds exciting. you know, when you say experimenting, it really puts it in a different frame, and it makes it more exciting rather than complicated. Because all of this for me is complicated. So if there are not any additional questions, I would like first to thank you, Maru, for conducting this session, for you joining, for all of you who joined, and we'll send an email afterwards with you know, the links to the recording of today's session and previous session, and also some resources that you can refer to, so that you can grasp better what we discussed today, and for you to be better prepared for the next session, where we will be experimenting, let's put it this way.
Okay, thank you so much. Really appreciate this. Thank you. Bye.
Bye for now. And yeah, you'll get information on when the next session is going to be held in the email that I referenced. So it's going to be a long email. Thank you everybody for joining today. Bye for now.
Thank you.
Thank you, Doctor.